Hello everyone. In this video, we're going to learn about how to find the determinant of a 3x3 matrix. So we have a video on our STEM Guide YouTube channel called How to Find the Determinant of a 2x2 Matrix. So before you watch this video, please watch Finding the Determinant of a 2x2 Matrix video to help you out more as you watch this video. But basically, as a refresher, we are going to review the formula for finding the determinant of a 2x2 matrix because it is useful and important when finding the determinant of a 3x3 matrix. Determinant of 2x2 matrix. So let's say we have the matrix A, B, C, and D. This is a C, this is a D. Okay, so this is a 2x2 matrix, right? Because it has 2 rows and 2 columns. Okay, and I'm going to undo this just to save us some space. So the formula for finding a determinant of a 2x2 matrix, and remember you write the determinant with these 2 lines. So formula for this is AD minus BC. And remember, this is only valid for 2x2 matrices, so you can't use this for 3x3, 4x4, etc. And this formula for finding the determinant of a 2x2 matrix will be extremely helpful in finding the determinant of a 3x3 matrix. So let's go over an example of a 3x3 matrix. And I don't expect you to know this. This is why I'm giving this video. Okay, so let's say we have matrix A, which equals 5, 3, 4, 4, 5, 2, -3, 5, and 1. So this is a 3x3 matrix. So we know that the formula for a 2x2 matrix isn't going to work on this. So we need to find the determinant of this 3x3 matrix. So remember, you write the determinant like this. So 5, 3, 4, 4, 5, 2, -3, 5, 1. So these 2 lines show that you are finding the determinant. Okay, so first we're going to treat this like a checkerboard. And if you're not familiar with what a checkerboard is, that's okay. And you don't necessarily need to follow this step. It's just a helpful visual for students to understand. So like a checkerboard, you have a black here, then you have a white, then it's black, then you have a white here, then it's black again, and the next piece is white, and there's black again over here, there's white, and then there's black. So you might be getting the idea of the pattern. It's like a checkerboard, it alternates black, white, black, white, black, white, black, white, black. So we can treat the blacks as positive and the whites as negative. So this is going to be positive, this is negative, this is positive, this is negative, this is positive, this is negative, and this is positive. So the blacks are positive and the whites are negative. So why is this useful? How does this pertain to our problem? Well, the blacks that are positive are going to correspond to the numbers on the matrix. So essentially, this is a 3x3 checkerboard, just as this is a 3x3 matrix. And when this piece, which is the first piece, is positive, the 5 is going to be positive. And this piece, which is positive, so 4 is going to be positive. So notice how these kind of are the same with each other. So this piece over here is the same as this piece over here. This piece is the same as this piece, and they both are positive. So the blacks are positive. So this is also positive because this is positive, and -3 is going to be positive because of this, and 1 is going to be positive because of this piece, which is positive. So if this doesn't make any sense, that's completely okay, but this is just something very important to keep in mind as we go through the problems. I'm going to explain this more. So then the other numbers are negative because this white is negative, then this one, which corresponds to this is negative, and this one is negative, then 5, which corresponds to this piece, is negative. So essentially, you didn't have to do the whole checkerboard thing. It just helps initially when you want to visualize it or if you want to remember the pattern. But essentially, you just have to remember that the first number is positive. Then you do negative, positive, negative, positive, negative, positive, negative, positive. It's just something to keep in mind. So I'm going to erase these annotations since it might be a little difficult to comprehend. Okay, so you have this matrix. So first, we are going to look at the first 3 numbers in the first row. So we're going to look at 5, 3, and 4, right over here in this row. So first, we're going to look at 5. So we write positive 5 here. Remember, 5 corresponds with this positive over here. Okay, so positive 5, and we're going to multiply that by something. We're going to multiply that by a submatrix. So what that means is that we're going to look at this 5. Remember, this is why we wrote positive 5 over here. So we're going to look at this 5, and we're essentially just going to put a line through the row that the 5 is in. So we're going to put a line through this row, and we're going to put a line through the column that that 5 is in. So we're going to put a line through this column. And let's look at the numbers that we're left off with. So we're left off with 5, we're left off with 2, left off with 5, and we're left off with 1. So these are the numbers that haven't been canceled. So then we put that over here. Actually, before I continue, I'm going to erase the annotations and then write, but remember that 5, 2, 5, 1 is our new submatrix. Okay, so we have 5, 2, 5, 1, as we determined earlier. Okay, then the next step. So we're still looking at the first row. So we got 5 done. Now we're going to go to 3. So am I going to write positive 3 or negative 3? Well, this is where students kind of, when they rush too much, they get a little tripped up on. So this 3 corresponds to this white square, which is negative. So this is where the negative comes from. So you're going to write negative 3, and you're going to times it by a submatrix. So you're going to times it by a submatrix. And what is that submatrix? So we're going to do the same thing as what we did with 5. So we're going to put a line through the row that 3 is in, and we're going to put a line through the column that the 3 is in, which is over here. And what numbers are you left off with? Well, you're left off with 4, 2, negative 3, and 1. So this becomes our new submatrix. So remember these numbers as, because of annotations and just because it might not look too clean, I'm going to erase it after. But 4, 2, negative 3, and 1. Okay, so I'm going to clear some of this. Okay, so as we said earlier, 4, 2, negative 3, and 1. Now, we're still looking at the first row, and we're going to look at 4, which is the next number. So we're done with 3, awesome, and we're going to look at 4. So is 4 positive or negative? Before you do this, you always have to look at whether it's positive or negative. So 4 corresponds to this square, which is positive. It's going to be positive 4. We're going to multiply that by a submatrix. So what is that submatrix? Well, you do the same thing as you did with this 5 and this 3, which is that you look at this 4 and you cancel out the row that it's in. So you're going to cancel this row out. So this row pretty much always gets canceled. And you're going to cancel this column out, the column that the 4 is in. So you're going to cancel this column out. So you're left with a submatrix. Submatrix is 4, 5, negative 3, and 5. These are the numbers that you're essentially left off with. So remember these numbers, 4, 5, negative 3, and 5. So 4, 5, negative 3, and 5. Okay, so now this is something that we can do. So remember, the determinant is not a matrix itself. The determinant is an actual number. So if we keep it like this, it's technically incorrect, but we're getting to the right place. So now what we know is that we've pretty much divided this into 2 by 2 matrices that we need to solve for. So I'm going to rewrite this whole thing on the next page. Okay, so I just rewrote whatever we had on this slide right over here. So I just rewrote all of that on this next page. Okay, so we have 3 2 by 2 matrices. So what we're going to do is 5 times, remember the formula for a 2 by 2 matrix. Let's just rewrite that over here. So the determinant of a 2 by 2 matrix. So A, B, C, D equals AD minus BC. Okay. So in this case, 5 is A, D is 1. So D is over here, A is over here, so A corresponds to 5, D corresponds to 1, B corresponds to 2, so B is over here, 2 is over here, and C, which is over here, if we go back to our matrix, is over here, right over here. So if we go to the next matrix over here, the 4 corresponds to the A, the 2 corresponds to the B, the -3 corresponds to the C, and the 1 corresponds to the D, which is over here. And our final submatrix, so the 4 over here corresponds to the A, 5 corresponds to the B, -3 corresponds to C, and 5 corresponds to D. So if we go back to this matrix, so we have our A, B, C, and D, so now we just have to plug it in. So you don't need that line over there because you're going to be multiplying it just as it is. So it'll be AD, so 5 times 1 minus, remember there's a minus sign over here, minus B times C, so minus 2 times 5. Then we have -3 times, so we have our submatrix over here, and we have 4 is A, 2 is B, -3 is C, and 1 is D. So if we follow this formula over here, then we have AD minus BC. So we have 4 times 1 minus 2 times -3. So be careful with this negative, and that's negative when you multiply. And then you have +4 times, and now we're looking at this submatrix. So we have 4 is A, 5 is B, -3 is C, and 5 is D. So if we use this formula right over here, then we have AD, so that's 4 times 5, minus BC, so that's 5 times -3. Okay, and this equals, so 5 times 1 is 5, and minus 2 times 5, so that's 10. So we have 5 times 5 minus 10, which I'll write later. 4 times 1 is 4. -2 times -3 is +6. 4 times 5 is 20. -5 times -3 is +15. So we have 5 times 5 minus 10, minus 3 times 4 plus 6, plus 4 times 20 plus 15. So this equals 5 minus 10 is -5, 4 plus 6 is 10, and 20 plus 15 equals 35. So we have 5 times -5 minus 3 times 10 plus 4 times 35. And in the end, because I'm running out of space and I know you know how to multiply, so you have -25 minus 30 is -55. And then 35 times 4 is 140. So -55 plus 140 equals 85. And this is your answer. It took a while, but this is your answer. The determinant of this in particular this 3x3 matrix is 85. So an important thing to keep in mind is that a square matrix is invertible if and only if the determinant does not equal 0. Okay, so remember that a square matrix has the same number of rows and the same number of columns. So if a matrix has 2 rows and 1 column, or has 5 columns and 1 row, so it's a 1 by 5, then it is not invertible. A square matrix would be something but like 2 by 2, 3 by 3, 4 by 4. But even if it's square matrix, it doesn't automatically mean it's invertible. You have to check for the determinant first. So if it's like a 3 by 2, 1 by 4 matrix, then it's not invertible. However, if the matrix is a square matrix, where the number of rows equals the number of columns, so you have like 2 by 2, for example, 3 by 3, 4 by 4 matrix, for example, 4 by 4 meaning where there's 4 rows and 4 columns, then there's a possibility, the huge word is possibility, it is invertible. So remember that it's not guaranteed just because it's a square matrix. So if we go back to our previous problem, where we found the determinant is 85, we said that a square matrix is invertible if and only if the determinant is not equal to 0. So we have a square matrix. So right over here, it's a little messy, but essentially this is our square matrix. It was a 3 by 3 matrix. So it's a square matrix. And it's invertible if and only if the determinant is not equal to 0. So we found that the particular determinant for this problem was 85. And 85 does not equal 0. So therefore, this particular 3 by 3 matrix is invertible. Okay, so thank you so much for watching. If you have any questions, please feel free to put in the comments and I'll try to answer them. I hope you learned something from this video, and if you did, please subscribe to this channel to have more educational videos. Thank you.